Okay. Hi, everyone. Thank you for making it to my talk this afternoon. Now, before I get started, I wanted to ask a few questions. So who here, can I get a raise of hands on anyone that's heard of Riak before? Okay. Of those hands, how many of you are using Riak at the moment in what you're building? Okay, good. So this talk should help shed some light on what makes Riak special. To get started, I want to explain who I am first of all. So European operations for Basho has been around for just over 12 months now, and I've been with Basho for about 9 months. I'm part of the client services engineering team, and that team is split into two halves. So I work on the team that is focused on application development with Riak. So if you have any questions about data modeling, or you have any relational schemas that you want to sit down and get some help with porting to a distributed key value storage engine like Riak, then that's the kind of thing that I spend a lot of the time focusing on at the moment. So that's a bit of my background. Before joining Basho, I worked in finance, so worked on JVM projects to build broker-neutral foreign exchange trading platforms, and worked a bit of C++ in there for some of the speed, real-time stuff. So that's a bit about me. So let's get back to what is Riak. So it's a key value storage engine, okay, based on research work presented by Amazon in their Dynamo architecture in 2007. It's distributed, horizontally scalable. It's fault-tolerant, highly available, and built for the web. Now, I'm going to go into more detail in how we achieve a lot of these features and explain that it's a lot more of an engineering feat than simple marketing. But as a high-level overview, it's a lot of this knowledge and technology piggybacks off research work into Dynamo architecture, and we like to consider ourselves a faithful implementation, open source implementation of that work, written in Erlang. But don't be scared off by that. We've got client libraries for a variety of programming languages, and I'll show you a little bit of Java code later on to help you get started with building applications on top of Riak. So key value, this is the fastest way, the most low latency way to access data in Riak. Very simple set of operations: get, put, delete. Unlike your relational model, you don't want your key being some sort of auto-incrementing ID, even if you use something like Snowflake from Twitter to generate those unique IDs. You want to use semantic keys as much as possible. So you want to make sure that what you build uses a key that is some sort of combination of, let's take a music application as an example, some sort of artist name underscore album underscore year of album, something like that. So that you want to make sure that the key itself contains semantic information about the object that you're storing. So the values themselves that form this KV pair that we store with Riak is mostly opaque. So we don't do any kind of introspection work for the most part. So you can store any content type you like in there, XML, JSON, binary, some other textual format, YAML, something like that. And we also allow you to store other types of meta information that I'll explain in more detail further on, that you can use to do additional indexing work on that data without actually needing introspection. So on top of pure key value access, you've got secondary indexes, and these are one of the parts of the, I guess, metadata region that we store with a KV pair. As with links, full text search is something that, like I mentioned higher up in that slide, that it's mostly opaque, but not completely opaque. So if you provide some sort of index schema of some kind, we will, if we can detect that its content type is some sort of textual representation, we will allow you to do term-based indexing on that data. So you can, this is really meant as a full text search engine of some kind. So if you want to search for particular keywords in a particular piece of textual content of some kind. Okay. Finally, I think many of you will have heard of MapReduce before. Can I get a raise of hands who's heard of MapReduce? Cool, perfect. How many of you are using Hadoop? Awesome. Okay. So MapReduce is technology that was, I guess, to some extent reinvented by Google in a couple of their research papers a few years ago. Well, more than a few now, but it's really based on 80s work done by functional programming languages based around the concept of a map function and a reduce function. It just so happens that those functions can be broken down and parallelized, so what we call embarrassingly parallel functions. And with distributed databases, you can then take advantage of the compute power that's not being harnessed by your relational query engine of some kind, your structured query engine, and query optimizer, and reappropriate that spare compute cycles for doing MapReduce work. I'll go into more detail about when you would use MapReduce and when you wouldn't, especially with respect to Riak. But that's basically in the heart of it. That's what you would use as the tools as an application engineer to compose the kind of data querying functionality you need, and therefore achieve the low latency access to your data that is going to scale your business. So all Riak objects are referenced by key. Keys are grouped into buckets. A bucket is a logical abstraction. In Riak, it's not a physical abstraction, so there is no, inside the data directory on disk, there is no bucket name that you can then do a delete on to delete just that subset of your key space. We actually treat the bucket name itself as a prefix when we actually store it on disk inside the storage engines. And the reason I point this out specifically is because doing a key listing operation, so the type of thing you do with your select star from table name that you're used to doing in a relational model, is extremely expensive in Riak because the bucket name doesn't contain any kind of special index. It's just a prefix on a key, which means that what we do is we walk the key space. So as much as possible, you want to be indexing using our secondary indexing functionality to be able to access parts of your key space efficiently. Okay, so this is essentially what the abstraction looks like in a nutshell. So, like I said before, it can be any type of content type you like. Typically, you store JSON. Most of our client libraries have built-in serializers and deserializers for the JSON format, but they're all designed in such a way that you can plug in whatever serialization format you like. Now, unlike many databases where you'd start with a single node and you'd start to scale your business up by clustering and sharding the database engine, in Riak, we're not a small-scale database. So when you start off with your database, we really expect you to be starting with a minimum of 4 nodes. Ideally, you'd be starting with 5 nodes because this gives the right balance between fault-tolerant and support for data growth at the kind of rates that we expect customers to be using Riak to build their business on. What makes it special is that query and load can be spread evenly. We don't have any kind of master-slave architecture. There's no write manager, no write coordinator, nothing like that. So you can round-robin requests by using a load balancer and maximize throughput across the cluster. So it's what we call always write available. So with that in mind, there's a very linear pattern to growth. So you can take the max number of ops per second that you get with that cluster, you divide by the number of nodes you have at the moment, and assuming you add another node with the same hardware, you're going to get more ops per second, more storage capacity, and more compute power. Now, one of the areas that we think that makes Riak particularly special, which is why we're in areas of healthcare, we're working with the NHS at the moment, and AT&T's mobile health project, and a bunch of other health-conscious and healthcare environments, is this fault tolerance aspect. And we achieve this by ensuring that there's no single point of failure in the architecture. All data is replicated. So by default, every single key is replicated to 3 physically distinct nodes. And this is auto-managed for you by the cluster. This means a cluster can transparently survive node failure, network partitions, and of course it's built on Erlang, which means that we piggyback off the fault tolerance that you get with that programming language and the Open Telecoms platform. So this means that you can actually hot swap. So if you have bug fixes or hot fixes that we need to release to you guys, we can provide them, and you can hot load that code without bringing down the node. And it sets Erlang apart from the JVM in that respect, although I'm pretty sure that with enough effort you could probably achieve the same with the JVM as well. Now, a great example, and I like to bring this up every time I give a talk somewhere, and you can find this tweet online. It's not something that we've made up. So Voxer are a customer of ours. They use Riak extensively. They're at one of these Node.js shops, and they do everything in an asynchronous callback model, and they have no single point of failure across their entire infrastructure. That includes load balancers, application servers, and database servers. So their walkie-talkie application allows you to record messages and pass over those voice recordings as though they're text messages, and someone can hear them at the other end. And anyone here use Voxer at the moment? Cool. So someone knows about Voxer. Cool. It's a very big thing in the US at the moment, and their CEO posted this on Twitter, Matt Rainey. And I'm not sure you guys can read it well enough, but nasty switch failure today took down 17 machines for 2 hours. Riak was slow but never went down. So with today's world where you're building your businesses in a cost-effective way and you're running on top of cloud infrastructure, these kind of network problems, server problems, data centers going down is a more common situation that you have to deal with than you might be used to. And dealing with a database engine that has a homogeneous peer-to-peer network of nodes allows you to cope transparently with that kind of failure. So as I mentioned before, we're inspired by Amazon Dynamo, so we share common properties with a bunch of other Dynamo implementations. Does anyone know, can someone shout out the name of another Dynamo-inspired database engine? Yep, Cassandra is inspired, and Project Voldemort from LinkedIn. They're both other Dynamo implementations, and we've all chosen different trade-offs to provide this fault tolerance at scale. But we share a common architecture, and that means that we're masterless, as I mentioned before. We use a consistent hashing algorithm, which provides an optimal lookup path over the network to your piece of data. That makes us extremely fast. We're all eventually consistent, and I'm sure many of you will have heard bits about what eventual consistency means, and I'll go through that in a little more detail. Quorum for reads and writes. So because we saw 3 copies of data, we basically only block on a subset of those read and write requests and do the rest of the work asynchronously. And the balance between blocking and non-blocking in this asynchronous distributed world is achieved by the Quorum algorithm that we use. It's a very straightforward algorithm, and I will show you in a few minutes. Finally, we use something called active anti-entropy, read, repair, and hinted handoff, to achieve this consistency by pushing the eventual state of consistency to a much shorter time window. So by having a background process that is constantly causing the database to converge, by making sure that out-of-date replicas are brought up to convergence as quickly as possible, we reduce that window of eventual consistency to as small as can be achieved over a network. So to go through the consistent hashing algorithm in a bit more detail, and to show you what makes these Dynamo architectures special. So we start by taking a key space of some kind. So in Riak, we use 160-bit integer key space. We then break that down into a number of fixed partitions. And these partitions are something that at the moment in Riak you define when you first set up your cluster. And at this stage, the defaults are well tuned for the right balance between cluster growth and performance on disk with I/O utilization. So in this case, for this example, it keeps it simple. We don't actually use 32 partitions. It's too small a number of partitions for the number of nodes that you typically have in production. But for this example, it makes the diagram look nice. So we break it up into 32 partitions. And we say that we're going to assign, in this case, to 4 physical nodes. So those virtual partitions, those vNodes as we call them, are managed by physical nodes. So there's this mapping of data partitions to physical servers. And whenever we do a write operation, we can walk that ring, that Dynamo ring, to ensure that we're writing the same record to 3 physically distinct. Okay, so that means that in the event of some sort of failure, we can guarantee that if this node goes down, these 2 nodes are still available to respond with the replicas that they have, and it also means that any new updates can be passed on to some sort of fallback node of some kind. And this means that we are doing our very best to provide high availability for your data. All of this happens transparently to you as an application developer with Riak. So, as I mentioned before, because it's a masterless system, there's no write manager of any kind. Any node can serve a client request. And so what we normally suggest people to do is use some sort of physical load balancer, something like Radware hardware, or a software load balancer like HA proxy, and round robin your requests across the cluster to maximize throughput. So fallbacks are used when a node goes down, and we always accept read and write requests. This sets us apart from these architectures that provide you with read replicas of some kind. So they provide you with some sort of slave environment, and they might have some sort of election algorithm that hands over master's status when the current master goes down. But there is still a window for data loss. And finally, per request quorums. So request quorums, we have n value of default of 3. This is completely tunable. So this is where we start to talk about flexibility of your data requirements. So if you're storing user account information, 3 or even more, depending on the number of physical servers you have, will give you the right balance between your data safety and performance in Riak. Then you've got read requests and write quorum, and they're calculated using nval over 2 floored plus 1. So if you've got a replica value of 3 and you want to find out what the quorum is for your read and your write requests, so how many of those are happening synchronously and how many are happening asynchronously, you basically take your nval, so 3 over 2, you floor that value, gives you 1, you add 1 to it, and then you know that your read and your write quorum is 2. And that changes depending on what you set your n value to for that data. And that n value can be configured on a per bucket basis, on a per request basis, or on a per cluster basis. So if we take a disaster scenario, so you lose some sort of physical server of some kind, and as I mentioned before, we've got a request, and in this case the blue node, node 3, ends up taking that fallback for that update, becomes a fallback replica manager for that update. Then the node, so node 0, comes back online, and then we do handoff to that primary replica manager, and you resume normal operations. Now, so a little bit of history for you. The early versions of Riak were actually built internally to support a web-based application that the Basho team were building. So this database was actually something that we were using internally before we ever provided it as a open source solution to the community, the tech community. And so for that reason, one of the first transport layers that we supported was a HTTP REST API. So we built some Erlang codes. If any of you is interested in learning Erlang, then there's a bunch of open source projects that Basho have released that will help you along the way with moving architecture over to Erlang. And we be as compliant as possible with the HTTP specification, but we actually loosen compliancy to actually make sure that reverse proxies, load balancers, and other web servers, they don't always follow the spec as closely as we do. So to make sure that that our HTTP response and request handling is well supported within the world of the HTTP, then we loosen that compliance level to cope with supporting all of these other HTTP-based infrastructure. And so in that case, it was built by us to be used on web applications. So if you're building a large-scale web application, there's no reason that it doesn't fit your use case as well. Other extras that we provide. So you can do pre or post commit hooks. So you can take a KV pair, so you're receiving some sort of JSON update, JSON record of some kind, and you can make sure that you do some pre-validation before you store that data, or you push some sort of cache invalidation mechanism after you've written that new update. Something special, I think, that we think is an important thing about a database engine is giving you the flexibility to handle multiple data problems that fit certain types of storage requirements. So with that in mind, we work with 3 different database engines. The LevelDB storage engine is built by Google, so if any of you guys use your Chromium browser, you're using LevelDB. It's a key value storage backend that Riak supports. Bitcask is homegrown. It's made by us, designed for your reference data of some kind. We've got an in-memory storage backend if you want some sort of data problem that is highly transient data, so temporary cache of some kind. And finally, we've got the multi backend, which actually allows you to chop and change between those storage engines, depending on the type of use case you have for that data. Which storage engine should you choose? So because I have a bit of a finance background, I like to try and give some examples that fit the kind of environment that I used to work in. So with Bitcask, I like to think that financial instruments fit very well into the Bitcask bounded storage problem. So you might have some sort of currency pairs that you're dealing with. New currencies don't get introduced into the global economy very often, so it's a bounded data problem. You're not going to see many different currency pairs popping up daily. So this great reference data problem to fit into Bitcask. LevelDB is for your unbounded data, so it's for your new web application that's going to redefine people's interaction with the world, and you're going to have a user base that's going to grow forever. That kind of data problem is something that you want to use LevelDB to store. Or if you've got any kind of advanced querying requirements surrounding secondary indexes or any kind of serious MapReduce work that you want to piggyback off 2i, which is the colloquial term we use for secondary indexes. Finally, in memory, I don't really recommend the in-memory storage engine very often, because any time that you would use the in-memory storage engine, you could really just use Bitcask, because it's essentially your persistent cache. So it's still written to disk, but the key space is replicated into memory anyway. But for certain use cases, you might want to fit just to inside the Erlang VM's memory space. And finally, no reason not to use it. The multi-storage backend. If you're starting on a big project and you're not sure whether you're going to have different storage requirements for different types of data, set yourself up with a multi-storage backend. Set the LevelDB storage engine as your default, and then as and when you need to set up any kind of Bitcask buckets or any in-memory buckets, you can do so and configure them as needed. All of this, by the way, can be controlled via the client libraries. So when the client libraries are instructed to create a new bucket, some sort of key space that key set that you want to store that fits inside your key space, then you can do that as you create those buckets within the client library. So how do you start designing applications with Riak? There's no intrinsic schema of any kind, so we don't enforce any kind of referential integrity between data. All of that is designed to be something that you deal with as an application developer. So your application defines the structure of your data. So in Java terms, this will be many plain old Java objects that fit your state problem of some kind. So it's your state package or your Pojo package, however you want to namespace your data problem, and the semantics of that interaction. So if you're doing kind of data aggregation work, and take a good example, so building some sort of web application and you've got users that come from the Facebook API, so you're doing data enrichment via Facebook, you might be gathering that user key space of some kind, storing those into your buckets, and then have some sort of background process bringing Facebook in to do data enrichment as those new accounts come online. That kind of problem is well suited to storing with LevelDB. You can build that in, and then as and when your JSON records become outdated, the update operations can happen through some sort of MapReduce phase, walking the key space and updating that from the Facebook API. Finally, as you will have noticed, that Riak doesn't have any kind of master-slave, which means we have no serialization mechanism of any kind. So this means that there are situations where you will have to deal with something called conflict resolution. So in the event of two concurrent actors, so you've got your application layer talking through your load balancer into your Riak cluster, you're taking two updates to the same key from two different application layer endpoints, you'll have a situation where you cause some sort of data divergence. Now, this is rarer than you might think, but in the event of network partitioning, it's possible. Okay? When this happens, Riak provides you two solutions to manage this kind of problem. The first one's a naive approach. It's last write wins, so we store a global timestamp with every update that we receive, and in the event of some sort of data conflict, we can basically pick the one at the server side that has the newest timestamp. The reason I describe this as a naive approach is because in any distributed system, you're going to have some sort of clock drift happening with your hardware. And we can't all have atomic clocks sitting in every data center to keep the clocks synchronized globally. So to keep things cost effective, then you're going to have to consider some other solution to your data conflicts. With that in mind, we produce something called a vector clock alongside each Riak object, which tracks changes that have occurred to that object. And so what we're able to do is detect when some sort of Riak object has diverged. And that means that two writers have caused an update to the same KV pair at the same time. So a vector clock, it's not as scary as it may sound. The other terminology in other NoSQL database engines might call it something like a Lamport timestamp. They're the same thing. Every node has an ID, and the last seen vector clock is passed through by the client library for every put and every delete operation. Riak will track the history of updates, a bit like version control of some kind, some sort of distributed version control. You can think about it as those GUIs that you see with version control. You can track the history of change sets. And if we can, we auto-resolve stale conflicts. So if we know that the newest update is a logical successor to one of the previous states of that object, we will automatically update that record. And that's where something called anti-entropy comes in. But if we can't, so in the event of some sort of merge conflict like you might see in your version control system like Git, we allow you to handle that conflict. So what will happen then is we store the collection of sibling objects, the divergent states of that object, and then when you retrieve that next KV lookup, you can do merge conflict resolution. So we give you a merge method with a list of objects, and it's your responsibility as the business domain holder to be able to merge those records down. So modeling tools: key value, link walking, full text search, secondary indexes, and MapReduce. So things to think about when you're modeling your data with key value: content types, denormalize as far as possible. So content types, you basically can consider that you can store binary. So if you're storing some sort of PDF document that's a result of some sort of invoice operation, then you can always put that binary straight into Riak. As long as these objects are under 1 megabyte, they're very easy for Riak to store. If they're larger than 1 megabyte, then our open source cloud storage platform that sits on top of Riak can handle extremely large objects and give you an S3 API. If you can denormalize your data as much as possible, this isn't always possible, especially with the interconnectivity of data in today's world. But if you can denormalize things into a single KV pair with a large JSON, embedded JSON record of some kind, then that's a way, a pure key value access to that data is going to be the fastest way for you to get it back. So like I mentioned before, meaningful application-specific keys as much as possible. So composite keys are a good example. This is a real-world example from a company called SEO Mods. They're a large search engine optimization company in the US. And for their ranking list documents, those are actually the sections they use to subcategorize that ranking list. So by crawler engine, locale, keyword, and then the URL itself. And now, as much as possible, you can time box your data. This is an interesting modeling technique that's a nice way of doing time series data in a distributed system. The idea is that you create buckets which represent 60 seconds, 2 minutes, 24 hours, some sort of time window of some kind. And when that time window is exceeded, then the new keys roll over to a new bucket space. And any of the old keys that sit in that old bucket can be then basically blocked together into a single key value record that can then be compressed by gzip of some kind and then stored into a single record that might be an end of day or an end of week record of some kind. And so you can continuously receive updates and then keep merging those time windows down again and store them into a bigger and bigger bucket. That's the technique that a company called Boundary used that as a customer of Basho's. Does anyone know Boundary? They produce a networking daemon that streams statistics about the network topology back to their central service, and then give you some great statistics on how your architecture is performing and what kind of packet loss you're seeing at certain different endpoints of the network. Finally, I like to call them index objects, but some of our documentation refers to it as references. There's no reason that your user account object can't store an array that is an array of keys of some kind that might be their friend list. And those keys themselves will incur new requests that you make into Riak that you might parallelize as much as possible through some sort of multi-get operation and retrieve them all together. So you grab the index object, you then walk the index object, deserialize it, grab those keys, then parallelize requests for those keys, gather your results set up in one go. That process of referencing to other keys, we don't enforce referential integrity. You can through a pre-commit hook if you want to write it, and it can fit your particular data domain. But we don't enforce it by default, and you can then use that as a way of basically more efficiently leaving your data set normalized to some extent, but then still being efficient enough in the retrieval process by doing the aggregation work at your application layer. So I haven't mentioned anything really about links at this stage. The HTTP specification defines a header in the header region of your request that allows you to ask the browser to prefetch URLs of some kind. So with this in mind, you can think of it like as a way of applying lightweight relationships like anchors between pages. So like I said, because Riak was originally built for the web through a HTTP REST API, we looked at this part of the spec and thought that this could be reappropriate quite efficiently for some sort of limited form of graph traversal. So these links allow you to include some sort of tag of some kind, and again, that's stored in the metadata region of your KV pair, and that's a link that needs to be established on both sides of an object. But you can say that this user object is a friend to that user object, and then you can start doing some sort of link walking operation, and you can traverse those relationships between objects and retrieve some sort of result set that you want at the end. Now, because it's part of the HTTP spec, there is a limit on the size of a HTTP header. So if you're using the HTTP transport layer in our client libraries, you will incur a limit of about 1,000 links that can be attached to a Riak object. Now, the protocol buffers implementation, which is our other transport layer, doesn't have any kind of limitation like that. But it's something to be aware of, that if you're using a HTTP client library and you start to see odd results where an object isn't being returned with the correct links to it, then it's probably because the HTTP spec is cutting off the end of that header after the 8 kilobyte limit. So full text search, I mentioned it a bit earlier, designed for searching plain text. It's not really designed as a document-based indexing engine. That's some work that we're doing at the moment in another project that we call we've codenamed it Yokozuna. And that work is direct Solr integration to Riak. So how many of you here are using Solr at the moment? Okay, well, it's currently under final stage development, but it's already available as a technical preview on Basho's website. And you can grab pre-built AMIs for EC2 or whatever and experiment with document-based indexing using Solr and the direct integration between Riak and Solr indexes. But built directly by Basho for term-based indexing is our full-text search engine. It's like Solr and Lucene, but very far limited in its ability to do document-style indexing. It's primarily focused for term-based indexing of textual data. So it automatically indexes KV pairs, so you add new data to a bucket or some sort of search bucket of some kind. You've already told Riak that you want to index that with your full-text search engine, and we'll go in and make sure that those indexes are kept in sync. That full-text search can be passed as inputs to your MapReduce phases. So if you want to do some sort of filtering work before you do your MapReduce work, you can do a search, pass those search results into MapReduce, and then do some compute work on that. And the index schemas are entirely customizable and redefinable through the client libraries. So secondary indexes, like I mentioned before, defined as metadata. Two types at the moment, either int or string. Integers means that you can do from and to ranges if you want to do your range queries. And strings means that we do string-based range operations. Again, they can also be passed as MapReduce, as key sets to your MapReduce jobs of some kind. Seems to be more common than what we see with a full text search. Very good for things like I want to produce some sort of end-of-day summary that might be needed to be sent to management or used in some sort of further analytics work, or you want to derive other semantic value from analyzing that data. You can definitely do your initial lookup through a secondary index query. Do that at scale, get your millions of records that are part of that key set, and then send them into your MapReduce jobs. So I've mentioned MapReduce roughly at this point, but let's talk about it a little bit more in detail. In relational databases, what you're used to doing at this stage is grabbing all the data you need out of the database, doing whatever compute work you need in your application layer, and then either storing the result back to the database or returning it to some sort of customer through some sort of web UI or desktop UI of some kind. Now, the problem with that approach is that it's quite costly when you start talking about gigabytes, terabytes, and petabytes of data. In many cases, a lot of that data just won't fit in your application layer while you're trying to do your compute operations. You have to invest a lot of time optimizing that work, and in some cases, it's just not possible to perform by transferring that data out of the database. So what we're trying to do is move the compute operations from being performed in your application layer to being performed by the database engine. And if you're using some sort of NoSQL solution, something that's schemaless, not focused on a structured query language, then there is empty compute cycles not being consumed by most of the interaction work you do with the database that could be reappropriated to some sort of MapReduce. So the advantages of MapReduce is that it scales more efficiently for large data sets, and it takes advantage of compute power that would otherwise not be used by the database. So in Riak in particular, you're always going to be network and I/O bound before you ever get compute bound. So it's designed for more involved queries. It can be used for doing large-scale data fetching from disk, but it's not really designed for that kind of work. It's mostly designed for introspecting on a KV pair, finding some sort of fields that you care about, grabbing the values out of those fields, and then adding them up, or doing some sort of multiplication or some sort of algorithmic complexity that you need some sort of final result to. You specify the input keys, some sort of key set, again passed in from a secondary index query, from an index object, or from full text search. Process the data in map and reduce functions, and those can be written in JavaScript or Erlang. I don't recommend that you use JavaScript for production use, because what this requires you to do is to basically send that function as a string into the database. The database will then parse it, so lexically walk it, parse it, build an AST for it. Inside the JavaScript VM, we actually use SpiderMonkey to do that inside the Erlang VM, and then cache that function so that it may then be used again sometime in the future while that node is running. That can be quite costly. If you do have them that they're written in JavaScript and you want them converted to Erlang, just drop us a note on the mailing list and one of us can rewrite it for you. It's not designed for real-time data processing work. So there's a reason that people use Hadoop to do deep dive analytics where you might get a result a couple of hours later by working on an extremely large key set. Riak's version of MapReduce is more of a scatter-gather type querying engine. So what you want to be using it for is some sort of rate-limited operations that are done with background workers during your application's lifetime. Okay, so you want to rate limit that to some number that's dependent on the number of nodes that you have in your cluster. So if you have a 5-node cluster, you might only ever be doing 30 or 40 jobs at any one time on the cluster. And you should be controlling that through some sort of job queue of some kind. So as I mentioned before, two different transport layers, HTTP and protocol buffers. If you're in production or you're concerned about getting better performance through the network, you really want to be using the protocol buffers interface. The only time I recommend the HTTP REST API is if you're going to put something like Varnish or Squid in front of it and just use that as a massive caching layer. That might be when you want to take advantage of the HTTP spec to allow you to use one of those HTTP caches. We officially support 5 client libraries at the moment. I've only put logos up for 4 there, but we support Python, Erlang, Java, Ruby, and PHP. And we also have a bunch of community-supported libraries and even people that have taken our Java client and built Scala wrappers around it, or Clojure wrappers, or Groovy, or Kotlin, or one of the other JVM languages. So this is a basic interaction model with the Java client library. So in this case, what I'm doing is I'm either instantiating the protocol buffers client or the HTTP client. You can obviously, using the Riak factory, you can pass in any kind of properties, IP addresses, port numbers that you want to configure your particular connection to work on. But these are using the defaults, for example. This is a standard process of creating a bucket of some kind. I'm forcing the n value here to 1, so I'm only ever storing one replica on some node in my cluster at this stage. And by turning siblings on, I'm also saying that I want to do conflict resolution on that bucket space. So when I receive records into that key space, I want to know that if I ever get concurrent write operations, you'll store those concurrent objects and make sure that I retrieve them to do conflict resolution if in the event of some sort of network partition. By the way, if there are any questions at this point, please just put your hand up and ask away. And finally, in the same vein as creating a bucket, I can just then go and fetch the bucket back if I'm somewhere else in the application layer, and you've got a fetch bucket operation. So once you've got that bucket, you can do your standard fetch, store, and delete operations. Deletes in Riak don't happen instantaneously. They take around 3 seconds for the storage engine to actually compress the data back down again on disk, because of the way we use these append-only style log-based data structures on disk. So if you try to do a delete and then very immediately do a get, you will see that you get a record back because the delete operation hasn't yet actually been compressed down by the storage backends. So it takes typically 3 seconds, but you can configure it to happen instantly. But that will cause a compaction operation on a delete. So with secondary indexes, what I'm doing in this case is I've already got my Riak client object of some kind. I'm doing a fetch bucket on my users. Once I've got the bucket that I want to work on, my user bucket, I'm going to fetch an index. It's an integer index named age. So I'm fetching for all users with a particular age from this range to that range. I'm executing that operation. That's going to hit Riak, retrieve a key set for a covering set of nodes that match my query, and then basically return to me the keys for those Riak objects. Now, once I've got the keys for those Riak objects, I can then, if I wanted to, pass it into some sort of MapReduce function. So here I'm doing an index query on a binary index, or a string index on emails in my users bucket, which match this kind of pattern, and then I'm using an Erlang function that I've defined, a reduce identity function that I'm executing to get a result set back. So some sort of compute operation that I'm doing on the cluster. So that's really the most complex end of querying from the client libraries. So you would use this compositional approach to building your data access layer, combination of pure key value access as much as possible, secondary indexes when you want to do kind of reduce the key space to some defined key set based on a particular pattern of either the key or some other indexes that you've attached on the object, and then I can either retrieve that result set directly from Riak or pass it into some other compute work that I'm going to do. Now, I want to go on a bit of a tangent at this point and talk about React Cloud Storage. The reason I mention it to you now is because we open sourced this last week. I think it was last Thursday, in fact. So it's now an open source product. It is your S3 protocol compatible cloud storage. So anyone who knows Amazon's S3 protocol will know how to talk with React Cloud Storage, because we are as S3 compliant as we can be. We actually test with Amazon's client libraries to ensure that we implement as much functionality as they have in that protocol at the moment. It's built on top of Riak, so it piggybacks off the fault tolerance and the distribution mechanism that we've built around the Dynamo architecture. But it also adds some other features like multi-tenancy and multi-billing, so you can set up cloud storage users which have a predefined amount of storage space available to them, and you can do billing work based on their usage, so gigabytes of data that they're storing into cloud storage. I'm working with a lot of different open source users and prospective customers actually who are trying to build kind of Dropbox style storage clones around their applications that piggyback off using cloud storage at the moment. So anytime you can think of React Cloud Storage as anytime you want to use Amazon S3, but you either have compliance reasons that force you to store these documents on your own data centers, or you just want control over your cloud. So you want to build your own private cloud space. So the cloud storage layer, for diagrammatic simplicity, I've blocked these together, but each of these actually sits on top of each of the React nodes. And what we do with cloud storage is we take a large object, send it through to one of the nodes that works as a coordinating node for that request. It then chunks that large object into 1 megabyte blocks and sends them into your React cluster under the hood, and that gets replicated to some subset of the cluster that is on 3 physically distinct nodes. So at this point, I want to wrap up very near the end, don't worry, 4 slides. So when would you consider using Riak? I can talk to you about customer use cases if you like. I can talk to you about open source users using Riak, and I'm happy to speak at the end if you have any questions about that. But the kind of environments you want to use Riak, generally speaking, anywhere you need this reliability and flexibility. So we like to think that we are distributed systems engineers that focus on data integrity at scale. And it's for that reason that we focus on these complex features like vector clocks and conflict resolution to ensure that you don't lose your data. You're given the opportunity to reconcile some sort of conflict operation yourselves and then make sure that it's resolved to a single value. So it's this care in looking after your data that we put at the forefront of anything else with our distributed system. If you've got a session data problem, so user session caching of some kind, those kind of use cases fit very well because they're always keyed on user account name of some kind anyway, or an email address, which is a globally unique thing anyway. If you want to serve advertising, I know that many of you will probably be thinking that means more ads onto my mobile devices, but we do have many open source users using a React cluster to provide mobile adverts actually into your devices. Logs and sensor data. I'm working with some interesting customers actually that are trying to build these kind of monitoring solutions for like eco-meters that sit inside of buildings and stream water meter readings, energy consumption readings, and that kind of thing into their data warehouses that they can then do this compute work on at the end of the day or at the end of an hour, and that kind of work fits very well into Riak because it's got that MapReduce functionality for querying and compute work, while at the same time has that high availability, which means that you can really get maximized throughput from many devices streaming data continuously into the cluster. Now, if you're building some sort of content addressable storage solution, then React Cloud Storage is a perfect fit for that kind of environment. Anyway, you need a private cloud of some kind, and ultimately wherever you need low latency, and that's going to increase your revenue in some way. This was the ultimate goal that Amazon had that forced them into designing the Dynamo architecture originally. They looked at their retail platform and they determined that the higher the latency was introducing lost revenue of some kind in their shopping basket, in their payment processing areas of their system. And so they knew that if they could lower the latency on a user's experience through their web service, then they could actually increase their revenue. So a little bit about who Basho Technologies are, because we're the sole developers of Riak. It's Apache 2 licensed, so you're welcome to fork it and build your own version of Riak, but as far as I'm aware, we're the sole developers of it at the moment. It was founded by a bunch of engineers from Akamai in 2008. We focus on building large-scale distributed systems. We develop Riak in an open-source way. We specialize in storing critical information with data integrity, and we've got offices all over the world. So if you would like to speak to us in London, for example, then you can always drop by our office. We've been, as I said, in operations now just over a year. Does anyone have any questions? Yeah, please. No, nowhere at all. Yeah. And then that means that you can then use something called key filtering as a way to filter down, to get more specific keys as a subset of that key space. Yeah, well, yes, and by using a certain level of detail into that particular key. So by walking that particular key and pick subsets that get reduced as you get more specific by walking that particular key, yeah. Yep. Okay, and if you want to know more, then we're happy to come and do a tech talk anywhere at your offices, or you can come in and we can do some whiteboard development work and data modeling stuff. Thank you.